pulses for what they are. Okay. So, we know we have an idea of how to make them. Now, let us look into details of what they are, who they are on, and understand their personalities and befriend them in this section of the course. Okay. So, first we will look at a formal description of pulses, then primer on Fourier transforms, and let us go from the time to the frequency domain with the help of this excellent mathematical tool, that is Fourier transforms. So, already I have brought up a bit of a view of what a pulse can be, right. It is an optical light pulse. So, every word here deserves attention. Okay. So, a light pulse, by which we mean a pulse of an electromagnetic wave. By optical, typically by optical we mean the region of the electromagnetic spectrum which consists of the visible spectrum between 300 to 700 nanometers. However, in this course we will also talk about near infrared pulses and possibly even pulses going to infrared and further down to mid infrared. Probably far infrared is not of much consequence in this course, but we will just take the liberty of using the same adjective optical pulses or light pulses for all of these, okay, optical and infrared pulses. So, please excuse me if the infrared is often implied in what I speak and I do not say it explicitly. However, I will try to make a point to say optical and infrared or near infrared light pulses. So, typically the wavelength region of interest here is from about 0.3 micrometers to 1 micrometer, that is 300 to about 1000 nanometers, or even a little longer. If it is mid infrared, we have 2, 3, 4 microns. Okay. So, all these spectral regions will be of interest here. So, immediately one may ask, what is so special about it? Why are we talking about these optical pulses? Yes, there is something special. It is not any personal prejudice, it is the availability of lasers which can operate in various spectral regions and how well suited they are for making these pulses, making such light pulses. So, indeed we have even today in this very advanced human era, if you wish, only a fairly limited number of options to create optical pulses, and it is an evolving subject of science and technology in order to make newer and newer and newer lasers with characteristics that we desire of them. But for this course, what we need is to consider is electric field oscillating in time. We are not worried about the spatial part. So you can consider this to be the electric field at any given chosen point in space where the wave propagates with a decent amplitude, and on the vertical axis once again it is the electric field. So, what we mask here somewhat deliberately so in this course is the fact that there is another field oscillating in phase with this, which is the magnetic field, which oscillates perfectly in phase with the electric field. Okay. We somehow are in this case, yes, prejudiced, you can say, about describing the wave or pretending as if it is just an oscillating electric field, which is because the media that we consider are essentially non-magnetic. But if you were to use a medium that is having appreciable magnetic properties, then you would have to consider the magnetic field and give its due respect, and it is not very uncommon. Many of the lasers and advanced lasers that we have use a Faraday isolator, which is essentially something which exploits the magnetic field and acts on laser beams through that. We will have a chance to see about that, but then typically in the discussion which follows, it is electric field as a function of time. Okay. And the pulse is therefore an oscillating electric field with a finite well defined envelope of this type, okay, and everything else is the oscillations inside. The oscillations inside are what we may call the carrier, okay, and the modulation on top is the envelope. So, there is a carrier and there is an envelope. So, if we were to imagine ourselves to be inventing a formal mathematical description for a typical laser pulse, this is the view graph, and we want to try and put this in rigorous mathematical language. Note here that we have deliberately varied the periodicity in time of the carrier. It is not necessarily the same time period going from left to right, right. So, this is now things getting advanced and serious, in the sense this is the more generic way of having a pulse rather than having a uniform carrier frequency all throughout, right. So, this should pique a beginner as to, oh, what is happening, right. Why did not you sketch a pulse with a uniform carrier frequency inside? Yes, that is a good question which I asked and answered. So, we want to keep this generic picture and take this forward in describing pulses or laser pulses, light pulses, optical light pulses formally. So, let us do that first. Okay. So, I have in the next view graph gone a step further and taken away that nice symmetry from the envelope. So, I have compromised the, if you wish, the beauty of the envelope by considering a relatively scratchy envelope of the pulse here. It does not look Gaussian anymore. Why should it be Gaussian and everything, right? So, it need not be that perfect if you wish. So, let us consider now a laser pulse. We have introduced plenty of things to discuss in just one slide. So, the first among which is the adjective ultra short in itself, which I will qualify now. It is just it is after all an adjective, but then the point being that this is my light pulse, an envelope, and within that a carrier. Here the carrier frequency seems to be uniform all throughout time, from about -30 to +30 femtoseconds, right. I am pretty sure most of us here would not even need me to remind you that a femtosecond is 10 to the minus 15 seconds, all right. So, this instantly tells us that the way this pulse is sketched, that the choice of femto seems to be appropriate for whatever spectral region that this pulse corresponds to be in. Okay. So, this pulse is also typically in the optical near IR region, right. Now, the envelope of the pulse has a certain functional form. This is the envelope here is the envelope of the electric field. All right. The orange envelope is the envelope of the electric field, but we have already done something a little strange, if you tell me that the way we have written the envelope function in the complete description of the pulse, the electric field of the pulse, the electric field of the pulse is E of t. So, please note that my E's may change in the view graph. It could be this script E or the other font for E. So, please bear with any interchanges. E of t is always the electric field. So, here it has an envelope which I denote by the square root of I t. The square root of I t is the envelope of this pulse. It is square root of I t everywhere, right. That is the envelope. Okay. Then there is the carrier. The carrier is here, omega naught of t, right. That is the yellow part. Ouch, okay, I undid. Can I undo? Okay, I do not think I can undo it. It's just 5 more seconds for the coloring. All right. So, then we do have the carrier. Okay. So, now that's the carrier has a frequency which is omega naught. In this case, it is identically the same throughout all time from 0, -30 to a +30 and so on, right. But then now things get a little bit more sophisticated. We have an additional function which I have deliberately introduced here, which we call a certain phase function phi of t. Right. This is an additional phase function in addition to the omega naught t term. All right. This is something we must pay careful attention to. Maybe we did not foresee this guy coming in. It has a physical significance which we are going to explore in this and the next lectures coming through. Okay. Now, we have the envelope, we have the carrier, we have the whole electric field. What this tells us is that the maximum and thereabouts of the field are sharply peaked in time. The fact that a pulse is sharply peaked in time is captured by the envelope which we have written as square root of I t. I have not yet clarified to you what is I, but it is written down over here that I is the intensity of the wave as a function of time. The I of t function itself is not sketched anywhere here. What we have sketched as the envelope is the square root of I of t, right. So, because I of t per definition is in SI units 1/2 C epsilon the absolute value squared of the electric field E of t. So, for us here this is the electric field. So, therefore, the envelope of the electric field is a function which is proportional to the square root of I of t. That is why we have written it this way. We have not even bothered to use a separate symbol for the envelope function of the electric field, not the intensity. So, this is field, whereas this is the intensity of the field. So, the intensity of the field is always related to the absolute value square of the field. We encountered earlier the term irradiance. We again use the symbol I for it. Right. Again, irradiance is also proportional to a square of the electric field. It will take us into a slightly digressed discussion if we were to put all these together in a formal context. We will do that as the course goes, but this is the definition of the intensity. The facts that I want you to observe here are the following. I of t is a function of time. right. This function has an instantaneous description to it. At every instant of time t, the function I of t, which again we have not plotted here, bear with me, we will have a comparison of the envelope of the electric field and the intensity in some slides to come. But this function is instantaneous. So, it means at every point in time it has a certain description, and that description is related to something that has to do with the instantaneous value of the electric field in time. Whereas, irradiance, right, or the energy of a pulse are quantities which could involve some kind of integral over the electric field in time. They need not be instantaneous, they could be a cumulative description of something. Okay. So, if you did not, if that came as a surprise or a bouncer, if you wish, ignore it, just please appreciate the fact that intensity is an instantaneous quantity, the way we have described it here as a function of time. Okay. Now, it is sufficient to take up this definition of the intensity. Whereas, you will hear at other times that intensity is the energy crossing a unit area per unit time across the beam. That is also a valid definition. All of these emerge from primary definitions of these quantities through formal electromagnetic theory, Maxwell's equations, and what goes into them further, such as the Poynting theorem, right. So, take me up on this and let us proceed. So, we understand now that intensity is a quantity proportional to the absolute value square of the electric field. Furthermore, please also come along with me when I say that intensity is more easily measured, okay, than electric fields, which can also be in some sense measured. After all, electric fields are real quantities. It is just a question of what detectors are amenable to. Okay. Irradiances, intensities, energies, powers of optical beams, laser beams are measurable quantities. They all depend on something to do with this the mod square or absolute value square of the electric field. Okay, that is good. So, we got hold of intensity, let us get hold of the phase term now. Phase is everything in optics. Okay. So, what is the phase term? Strictly speaking, the entire argument of the complex exponential function is the phase, is the total phase. This total phase depends on time. So, in the language that we have developed, this therefore, this argument to the complex exponential function is also instantaneous. All right. Now, in the current scenario, we have chosen to write this composite phase function as a function of, which is a function of time, in two pieces. One piece where we employ the notion of a carrier frequency omega naught. What do we mean by the carrier frequency? It is the frequency of the carrier of this wave, of what we designate as the carrier of this travelling wave, whereas phi of t is an additional phase, the rest of the phase term. So, you could well say that this captures one part of the linear term in the complete description of the phase function phi of t. The rest, whatever is not captured in this omega naught t term of the total composite phase, which is a function of time, is phi of t. All right. That is the definition of phi of t. But what is it? I seem to be holding a mystery here at this point, right. But so be it, there are going to be no mysteries, we will resolve all of them as we discuss this through. But this is really an important piece of discussion and information that we must look through, because a whole lot of things depend upon getting this description right, and then we will see everything else is unwrapping and peeling things off and figuring out the details and minutiae, which are also very interesting, by the way. But then the rest we know, we have a factor of half plus the complex conjugate coming up because we want to keep the fields real, alright. So, that is the complete description of the electric field of the pulse, alright. Actually, I would deliberately want to pause even at just this one slide. I do not mind deliberating on this for a few more minutes over here, should you have questions about this either in person or online. Yes, good point. So, Aditya asks, why can't the carrier frequency be time independent? Here omega naught, by the way, I should have mentioned it, omega naught of course is a constant in time. So, why can't omega naught depend on time? Any thoughts, any ideas? Yes. So, the point is that the carrier frequency is constant in time only if this function is a constant. Otherwise, the definition of the carrier frequency as just omega naught t gets compromised. This is something we will see, okay. This is the previous view graph, the carrier frequency is not constant in time here, it goes from a low to a high, right. Visually, I am just asking you to do some visual estimate from this is one period, the period of the wave is shrinking as we go in the direction of increasing time. Yes, Amna. So, earlier elsewhere we may have written the electric field as E naught, say we used cosine here. So, k dot r minus omega t, and there I think we used theta to be, theta is independent of time. So, theta was the initial phase, we called it the initial phase, we also gave it the name the absolute phase, remember. So, here omega was, if anything, the equivalent of the carrier frequency. So, let us even make it omega sub 0 or omega naught. So, these two have the same meaning, the elementary travelling infinite plane wave with carrying just one frequency, the spectrum of this wave has just omega naught, amplitude only at omega naught or omega 0, right. So, this simplistic wave and this share the same notion of a carrier frequency here at the moment, but the fact remains, yeah. So, was your question that?
Does the time dependence of the phase somehow?
Now, the time dependence of the phase factor. So, if I now set this, consider just any one a given point in space and forget about k dot r as a consequence. I mean, sine is an odd function, so I can just write it as omega naught t plus theta, theta is independent of time, right. So, then this is the total phase term, and what do we observe of this total phase term? This phase term is identical, the phase term at the bottom here is identical to this, provided phi of t is just a constant and it has absolutely no time dependence. Then we are talking the same thing, right. So, the carrier is unchanged. However, if this has a dependence on time, then what is the difference between the expressions that we have here in this yellow box and the expression that is highlighted over here. What is the difference if phi of t had a time dependence, non-trivial time dependence, that is it is not constant in time. Then what is the difference between the phase at the bottom and this phase term here? Well, you are saying that the propagation of a point of constant phase will be towards increasing x as t increases if the description is kx minus omega t.
Now overall phi will be remain same.
That is a point of constant phase. The phase can have any value between 0 and infinity, that does not matter. Okay, although there is a periodicity with respect to 2 pi, but I get the notion that you are talking about, which we described, which we discussed in the context of phase velocity. A point of constant phase in kx minus omega t will travel towards the increasing values of x because of the negative sign and decreasing values of x for if we had kx plus omega t, right. Okay, so what is the point you are making, Ritesh?
I see.
Plain simple observation of these two phase factors, right. Just an observation of the two phase factors is all I am requesting you to do. What do you mean by frequency? You have to tell me that too. Yeah, you can define it, go on. What do you mean by frequency? Okay, roll back a few lectures. We stated all this fairly rigorously, okay. We stated all this fairly rigorously. We said that frequency, okay, is minus the partial derivative of the total phase function phi with a negative sign to it, okay, and the time derivative of that is the angular frequency. So, apply this definition to it here, to these cases. We realize that in the case at the bottom, the box at the bottom here, I take the total phase function omega naught t plus theta, theta being constant in time. Here if I do this time derivative, okay, frequency being negative or positive, it has physical frequencies are only positive. So, we should define them carefully. The time derivative of this is constant here, whereas if I now take the derivative of omega naught t minus phi t, here it need not be constant in time, or in other case here the frequency is linearly the phase is linearly dependent on time, whereas here we have overstepped the fact that, or we are deliberately going beyond the fact that the phase term is linear. It need not be linear. Why should it be linear in time? Why could it not be quadratic? Why can't it be cubic? All these questions come to mind, and these are the questions we want to raise, right. In fact, there is, if I may wish, since okay, I thought we will take a 10-minute interlude. So, in fact, there is another nuance hidden in this. Okay, we compared these two terms and said that look, in the simple waves case which Amna brought about, that the phase function is linear in time. Here it is not linear in time. We are throwing away that restriction. That also has another consequence. Yes.
So here we are saying it's like we are recording of phi of t, but we can also say it as superposition of different electric fields.
You are welcome to do that, which we will do. It is perfectly legal. Okay, the point being the following, right. We do not know what is phi of t. If we do not know a function, if we do not have a complete analytical description of a function, what do we often do? We would Taylor expand it. Now, when we Taylor expand phi of t, there is also going to be a linear term in t in the Taylor expansion. So, then in this entire description of the wave, we would have a term which has a linear, which is linear in t, we pull that out, and this phi of t is going to yield another term which is linear in t, alright. So, we have two terms linear in t. So, this guy here, the other term which is linear in t would be the first partial derivative of this at, let us say, some instant of time, say t is equal to 0 or whatever. So, let us call this some delta omega naught of t. There may be a sign, I may miss a positive or negative sign, but do not worry about that, frequencies are positive. So, we would have two terms which are linear in t in the entire total expansion of this composite phase function. Yes, that means we earlier took recourse to the similarity between the expression here at the bottom and this composite expression at the top and said that whatever is the linear aspect of the phase function, the linear contribution of the phase function, that is my carrier frequency. But now I am adding another, say, delta omega naught to it by Taylor expanding phi of t, right. Yes. So, that means we have two contenders for the position of the carrier frequency, an omega naught and what I call delta omega naught, which is a bit deliberate, by the way. So, this is some insight, we will realize this in the coming discussion. So, what is delta omega naught? It is there, if it is anything beyond linear and there is a function that captures the deviation of the phase going away from linear, the total phase going away from linear, its Taylor expansion has a first order term. Now, herein we are pushed to apply some logic and then say that, look, this is also a sort of perturbative analysis of the entire scenario, and omega naught is substantially greater than this delta omega. Alright, omega naught is substantially greater than delta omega. Only then defining or calling omega naught the carrier frequency has any meaning in the first place. So, the variation of phi of t in time is I am looking for an adjective. Pardon? No, here it is ultra slow compared to omega naught. 1 over omega naught or 2 pi over omega naught corresponds to a certain period in time. This function phi, its variation over that period 2 pi over omega naught is rather more gradual or slow as compared to sine of omega t. That is why I said this graph is very nice. Have a look at this. Here let us pick this optical cycle and call this frequency, this is a certain period t, let us call this t0. Okay. So, let us choose omega naught to be 2 pi over t0. There is a t1, there is a t2, there is a t3, there is a t4 and so on and so forth. I am biased towards t0, but it does not depend, it does not matter what I choose. I could have defined omega naught as 2 pi divided by t1 or t2, it has very little consequence. The fact is that this in the case of this pulse, the carrier frequency is not constant, but it has an upward slope in time, the carrier frequency. The phase on the other hand is not linear, it is deviating away from linear, it is parabolic, say t square, it goes as t square. So, what we are therefore saying is that we are capturing the deviation, let us say, let us take the phase, you are capturing the deviation of the phase from a linear value by using this function phi of t, right. Now, the fast oscillation part is the carrier always. Let us develop this notion and intuition, it would be very useful in this course. The fast oscillation is the carrier. All other oscillations must per definition be slower than that or more gradual, otherwise the carrier has no meaning. Right. Later on we will see the same notion can also be applied to spatial variables. Okay. So, this will lead to in certain treatments something called the slowly varying approximation, which is very useful in pulse description later on. We can anticipate this with all this sort of deliberate foray into some maybe intuitive discussion.
Is it impossible to vary it faster, like why?
It has a meaning only then. What is the difference between, say, if I may take the example of human experience, what is the difference between a salary and I do not know, pocket money? And if go back a few years, roll back, what you had as a younger person was pocket money, or even now possibly you do not have a salary, right. What your parents earn is a salary, and unless you are of course you have every ability to exceed that, but in terms of family income there is a main source and there is some part of it. So, we can look at it that way.
I understood it, sir, but the constraint that omega has to be greater than delta omega naught, is it like physically impossible to?
Otherwise, omega has no meaning. If you earn more, you would be the breadwinner of the family. Maybe you are keeping it a secret, but that is another matter.
Why is it called the carrier wave?
Yeah,
What
okay.
is carrying?
It is carrying, it is the thing that is propagating, it is carrying everything that is about the wave. Okay, go back even a step further. I do not mind, as I said, doing only one slide in this lecture because it is really important, one of you. The point being that if you had, remember this problem that you had in earlier studies, I am certain you did if you have gotten through Indian education, high school education. So, you take two waves, any two waves, electromagnetic or otherwise, we were told that okay, you take two waves whose frequency are apart by omega and omega plus minus a delta omega by, sorry, not, this is three waves, omega naught minus delta omega 2 and omega naught plus delta omega 2. So, let us write the pair like that. These are two waves, and how does their propagation look? This is a done and dusted problem in life, right. So, if this was, then you define the 0 of the electric field to be like that. This is the beating of the two waves, is not it? This is a lot of notions go back to this. That is why I want to hold, peg ourselves back to this. This is the envelope function. Alright, now we have two periodicities in time over here, is not it? We have this periodicity in time t, let us call this small, and we have the other periodicity in time t big. the bigger periodicity belongs to the smaller frequency delta omega, whereas the smaller periodicity corresponds to the bigger frequency omega 0. Now, you have the notion of a carrier wave. Why? Because there is another slowly varying or modulating function over here. We could have had this to be in a slightly different sort of perspective, omega naught minus omega say m by 2. I am changing the symbol, but this is something we will encounter in this course. This is just a modulation of this wave. What do I mean by that? This wave is propagating through something and I am modulating this wave deliberately. The LED lights in this room are being modulated at 60 hertz by the AC frequency. We are not able to perceive it, but if we had, there are scenarios where we indeed can perceive that, like a fan or something, rotating through it, and we observe some beat frequency of the rotating fan blade and the chopped light through the fan blade, which you often see is a variation at the beating frequency of the fan and the 60 hertz, right. We have 60 hertz here, yes, yeah, it is 60, it is maybe 100 elsewhere. So, that is the modulation. So, you can view it that way. So, you have the main frequency, the carrier, and the modulation, which is omega m, or here I am calling delta omega. Now, all we are saying in this case is that the modulation frequency also need not be the same across time. All right. Okay, so much for that. I will use my remaining 10 minutes to make some progress. Okay, but this is very important. That is why I said these concepts are the next hour or two are going to be about elucidating this. So, if we are unclear about something over here, it is going to maybe cost us a bit later. So, let us keep this notion of the pulse very straightforward in terms of all these details for the moment. Okay.